Hi everyone, my name is William Kumar Moses Jr. and today I'm going to talk about efficient dispersion on an anonymous ring in the presence of weak Byzantine robots. Now it's a mouthful, but I'll break it down in the minutes to come. This is joint work with Anisa Rahmanmolo and Kaushik Mondal. So, what's this talk going to be about? Well, first, I'm going to sell you on why you should even read this paper. Once that's done, I'm going to build up this model. I'll explain the problem statement, the model, and what our goals are. After that, step by step, I'm going to build us up to the final algorithm. Take us from a naive algorithm, explain what fails, and build us up. And finally, I'll wrap up this talk with some conclusions and a few open problems to consider. Now, first off, why should you care? Well, let me bring your interest from general computer science down to the specific problem. First of all, why should you care about mobile agents on graphs? Well, this deals with computational agents, typically limited in memory, mobility, and communication. They're working together to solve some problem. Now, this is a good abstraction for many problems in the world, whether you're dealing with actual robots moving around, or whether you're dealing with software agents in a network. So that's why we studied that. The specific problem of dispersion, well, that's actually interesting because we study this problem when we want to look at multiple agents that have to share resources, specifically when the cost of sharing those resources is much more than the cost of simply moving around and finding an unshared resource. Finally, why do we even care about these Byzantine robots? Well, in the real world, things fail, and things can fail catastrophically. And that's the notion that's captured by Byzantine robots. Furthermore, why should we care about it in this setting? Well, in all of mobile agents on graphs, this notion of Byzantine robots has only been studied within the context of gathering. And that's very interesting. But beyond that, there are multiple other problems that haven't been explored in this context. So, what are we doing in this paper? We're introducing Byzantine robots, this notion of Byzantineness, into the problem of dispersion. We're formalizing the problem statement, formalizing the notion. We're formalizing the powers that the robot may have, because you'll see shortly that's not trivial to define how strong or weak the Byzantine robots are. Finally, after doing all of this, we'll give a time and memory optimal solution for a ring. Now, it should be briefly noted that, as I mentioned, there have been solutions for gathering in the context of Byzantine robots. The thing is, a lot of those solutions are not time and memory efficient. So what we're doing here is, even if we do use gathering as a sub-procedure for our solution, but we do it much faster than these other papers have. So that's why you should read this paper. Now, let me explain the problem and what's going on. First off, what's regular dispersion? Well, I have an n-node ring, and I have n robots initially arbitrarily placed on that graph. And the goal is for these robots to move around such that there is exactly one robot on each node. And after this configuration is reached, the robots terminate. Simple enough. Now, what happens when you introduce Byzantineness into the picture? Well, of these n robots, up to f of them are Byzantine. And our final configuration that we want to reach, what we want now is, instead of each robot occupying exactly one node, we want to discard the Byzantine robots and we focus only on the non-Byzantine robots. And we want, for the set of all non-Byzantine robots, each of those robots should only occupy one node. Or put another way, no node should have more than one non-Byzantine robot on it. Once such a configuration is reached, we want the robots to terminate. Now, let's get into the model. What's the general setup? As I mentioned, you have an n-node ring, and you have n robots. Up to f of them are Byzantine. Now, the robots, they know the value of f, and they know the value of n. Furthermore, the number of Byzantine robots, f, is upper bounded by this value, n minus 4 by 17, floor of that. Now, the nodes do not have any IDs or identifying marks, but the robots have unique IDs taken from the range 1 to n. That is, there are n robots. Each of them has a unique ID, and it's from 1 to n. Now, between two nodes, each edge has port numbers corresponding to each of those nodes. I'll briefly show another picture here. Look at the node on the lower left, and you'll see that it has two edges going out of it, and port numbers 0 and 1 have been assigned to those edges. Now, there's no orientation to these port numbers, so they can be placed in any manner, but the numbers will be from 0 to the degree minus 1 of the node. Furthermore, all nodes are initially awake. Let's look a little more into memory time and Byzantineness. So we're trying to optimize two metrics here. One is memory, the other is time. What does memory mean? Each robot has two types of memory. Exposed memory, which is the memory that can be looked at by others, and unexposed memory, which may be considered its working memory. That's private and cannot be seen by other robots. And time proceeds in rounds, where each round consists of 3 stages. First, all robots that are co-located on the same node instantaneously and simultaneously read each other's exposed memory. And they may perform local computations and update their own unexposed memory. After that's done, robots then update their exposed memory. Finally, robots can either move to another node or stay in their given node. Now, coming to what it means to be Byzantine, more specifically weakly Byzantine, well, they're Byzantine because they can write, a Byzantine robot can write an incorrect value to its exposed memory, and it can move incorrectly. But why is it weak? Because in the exposed memory of a robot, its correct ID must be there at all times. These robots cannot fake their IDs. Furthermore, during stage 1 of each round, a Byzantine robot cannot change its exposed memory. Now, let's look at a few nuances of this model. They're needed for the algorithms that we develop later. First of all, robots can have a sense of direction, but the sense of direction, we define it as follows. Initially, when a robot sets its sense of direction, it looks at the ports around it, and the port with the lower port number is considered clockwise, and the other one is considered counterclockwise. And after that, this sense of direction can be set and unchanged. So even if a robot moves to another node, it'll maintain one direction as clockwise forevermore, and the other as counterclockwise. But using the technique that we described earlier, sense of direction can be reset, and we make use of that in our algorithms. The second thing to notice is when a robot moves through an edge, it knows both the outgoing port of the node it leaves and the incoming port number of the node it enters. Furthermore, if a robot is present on a node in round I, and it stays on that node even at the end of round I, it does not move, then it can observe how many robots are entering through the ports of that node in round I. So suppose this green robot is there in round I, and it sits there. Then what it sees is 4 robots came in through port 0, and no robots came in through port 1. Finally, we have a certain primitive that we use. It's called the follow primitive. And what it allows is the following. If robot A chooses to follow robot B, then wherever robot B goes, robot A can follow it. And that is even if robot B is a Byzantine robot, it doesn't matter. Robot A will always mimic its movement. It's somewhat of a strong primitive, but we do have other algorithms which are not presented in this talk, which allow us to solve this problem without resorting to this primitive. But for now, you should know this. Now, what are the goals of this paper? Well, I told you it's a time and memory efficient algorithm that we develop. So what does that mean? Well, from an initial paper in this area, a lower bound on time in a ring is omega of n rounds. And there's a lower bound that for any deterministic algorithm for dispersion, each robot needs at least omega of log n bits of memory. So what's our goal? To get an O of n round algorithm where each robot requires O of log n bits. And this algorithm should solve Byzantine dispersion. Great. Now, let's look at this algorithm. Let's build it up step by step. First of all, let's start with a very simple, naive algorithm. Here we have a 3-node ring, and we have 1, 2, 3 robots. What's the simplest thing we can do? Initially, if a node is unsettled, that is, no robot has committed itself to that node, just have the robot with the least UID settle down, and have the remaining robots move clockwise. Now, in this figure, what would happen? Well, robot 1 will settle down, robot 3 will settle down, robot 2 will move, and bam, it's done. But what's the problem? When you have Byzantine robots, they can lie. And what does lying mean? It can mean that while one says, I am the least ID guy here, so I'm going to settle down, in truth, it will move with robot 2 to the next node, and it'll block robot 2's attempt to settle down there. And this will continue until we're right back where we started. So how do we fix this? How do we bypass it? Well, remember, I said that robots cannot lie about their IDs. So if you can observe that robot 1 said, well, I'm going to settle down here, and it follows you, you know that it's a Byzantine robot. So if you can just remember the ID of all the Byzantine robots that you've seen, robots that have claimed to settle down, well, then you can identify Byzantine robots and settle down yourself. Now, the problem is there could be at most O of n Byzantine robots. And how many bits does it take to remember one robot? Log n bits. So you run into the problem of too much memory. But is there a way that we can use very little memory and still achieve dispersion without having to remember these IDs? Well, it just so happens that we have an algorithm where if all the robots were initially gathered, a simple algorithm allows us to disperse them. To be more specific, if all the non-Byzantine robots are initially at a node, this algorithm allows those robots to disperse without a problem. And it's a very simple algorithm. Look at this node that has robots 1, 2, 6, and 8. What will happen is these robots will communicate with each other and figure out a total order of their IDs. And it'll figure out which position they are. Based on that position, they'll move accordingly. So robot 1 is the lowest, it'll stay at its node. Robot 2 should move to the next node. Robot 6 should move 2 nodes down. But 6 was Byzantine, and so it didn't act accordingly. Robot 8, it sees its highest in this list, and so it moves 3 nodes down. It's a very simple way to achieve dispersion using only log n bits of memory. The only catch is all the non-Byzantine robots have to initially be at the same node. So then what's our goal now? How do we gather? How do we get all these non-Byzantine robots to be at the same node? Well, a simple idea is use one robot to collect the others. And what do I mean by collect? Well, look at robot 1. If it were to move around and get others to follow it, remember, follow is a primitive we have. One can keep moving around and eventually arrive at a position after it's made one full traversal of the ring where all robots that were non-Byzantine would have followed it. And now all non-Byzantine robots are co-located at the same node. Simple enough. But here's a problem. In the previous example, everybody followed robot 1. What if robot 1 was Byzantine? All it has to do is do nothing, and then we're stuck. So how do we get over this problem? Well, instead of just relying on one robot, what if we had a group of robots, a unique group that would move around collecting people? Now, here's the thing. If I have a group of at least F+1 robots that are guaranteed to be non-Byzantine, then if I am guaranteed that such a group is moving around, I, as some other robot that doesn't belong to this group, can just sit and wait until such a group comes by. Then I join it and move with it. Now, why would this work? Well, there are two things. One is there should be a unique such group that's moving around. And two, there should be at least F+1 non-Byzantine robots in it. Because we know that if there are only F Byzantine robots, and so even if all the Byzantine robots gathered together, they couldn't form such a large group. So what's our goal now? Previously, we were trying to gather robots. Now what are we trying to do? We've broken that problem down into a simpler problem of we want to uniquely form one group of at least F+1 non-Byzantine robots. Or another way to look at it is, can we uniquely form a group of at least 2 F+1 robots? Because it's guaranteed within such a group, F+1 of them will be non-Byzantine. How do we do this? Well, there's a simple two-step algorithm we use. First of all, recall that they're F robots. So, initially what we do is, we have all robots with IDs in the range 1 to F+1 go around this ring and collect any robots they can see. And if you'll recall, at least one of the robots in this with such an ID should be non-Byzantine. So at least one of them would have made the trip around the circle. Now, you'll have at least, up to F+1 such groups of robots. Our second goal is to gather all the non-Byzantine robots into a unique group. And it's very important that it's a unique group. The way we do that is we have all of these up to F+1 groups. If they're sufficiently large, they'll split up and they'll move around until they find robot 1, that is robot with ID 1. And the way we set this up, eventually, enough robots will find robot 1 such that there'll be 2 F+1 robots in that group. And those 2 F+1 robots will act as our unique group. Now, just to give you a visual representation of step 2, if I have a large enough group, how do they go about finding robot 1? Well, first off, that group breaks up into 2 smaller groups, evenly divided. And first, one of the smaller groups breaks up again, and one goes clockwise, one goes counterclockwise. After this is done, those 2 smaller groups also continue to move in their respective directions, while the group that previously sat at the node also breaks up and moves on. And then these robots move around the ring for n rounds. Now, at the end of this process, you will eventually arrive at a situation where at least 2f+1 robots will belong to the special group, which is the group that's found robot 1. And then we're good to go. Because once that's happened, you can send that group of 2f+1 robots around to collect all the other robots. So in order to recap this algorithm, what are we doing? First, we create groups, up to f+1 groups of robots in n rounds. Then we're trying to collect at least 2f+1 robots into one unique group. The uniqueness is centered around their attachment to robot 1. This takes a further n+1 rounds. After that, these 2f+1 robots have to move around the ring and collect all the other robots. That takes additional n rounds. Now, at the end of these 3 steps, what will happen is we'll have all the non-Byzantine robots gathered together at the same node. Then we can use the algorithm from earlier, rooted ring dispersion, to disperse them in additional n-1 rounds. Thus, we're able to solve Byzantine dispersion in O of n rounds, where each robot only requires O of log n memory. Great. Now we've looked at the algorithm. Now, very briefly, in this talk, I've only talked about our main algorithm. However, we have also been able to reduce the number of assumptions we've made at the expense of either the optimality of time or the optimality of memory. More specifically, we have a memory optimal algorithm, but it takes more time. But in that situation, f doesn't have to be known. It could be as large as n-1, and we don't require this follow primitive. We also have an algorithm which is time optimal, but memory blows up a little. And there, f doesn't have to be known, and it can be as large as n-1. We don't use follow, and the IDs, they're not restricted to this 1 to n range. It could be much larger, 1 to poly n. Finally, I want to conclude this talk by giving 2 open problems. First of all, as I showed above, we have other algorithms that reduce the number of assumptions. So can we generate, one interesting problem is, can we have a time and memory optimal algorithm that doesn't make use of any of the assumptions, or at least lesser number of assumptions than we previously used? The second thing is, we only focused on rings here, but is it possible to generate an algorithm for arbitrary graphs? With that, I'd like to conclude. Thank you.